objective number 4, this is to describe a process called neural integration and the role of the axon hillock in this process. So the axon hillock, if you remember, this is pretty much that neck region of the neuron. It's the narrowing between the soma and the axon itself. And we talked about this loosely earlier, where we said pretty much that graded potentials happen proximal to the axon hillock or before the axon hillock, whereas action potentials begin at the axon hillock and travel down the length of the axon. And so the axon hillock is really the region that determines whether or not that threshold value is achieved, whether or not that condition is met, and we can indeed fire an action potential. And so we're going to talk about neural integration here. This is the process of figuring out whether or not we meet the requirements, we meet the threshold value to bring about an action potential. And that involves a couple of different processes. So there's summation. We already kind of discussed what summation is. We can add different graded potentials. If they're close enough in space or if they're close enough in time, we can add them together to determine if that brings us closer to threshold. There's also the idea of frequency coding, right? If we speed up the frequency of action potentials, this translates to more neurotransmitter, which can increase the degree of our signal, the degree of the action, the degree of the neurotransmitter released and the graded potential on the subsequent neuron. There's also the idea of divergence and convergence, because we have a lot of different neurons synapsing onto each other and onto other neurons. We have this idea of splitting a signal, which is divergence, or congregating the signal, which is convergence. And we'll talk about what that is. And so all of that kind of is just calculated or assessed at the axon hillock to determine if we get to threshold or not. And that's what neural integration really is. So an action potential is going to be triggered only if we get to threshold, and that is determined at the axon hillock. And if we don't have that threshold value, there will not be an action potential. And so neural integration is deciding whether or not we have that threshold value using all of the mechanisms, taking all of those mechanisms into consideration, and then assessing the membrane potential value at the axon hillock. And so here we can see the illustration of divergence versus convergence. So divergence is pretty much splitting of the signal. So we have one axon synapsing onto several different neurons. And so we've got the separation of the signal into many different synapses on many different postsynaptic neurons. And we could think about the opposite type of coordination. So convergence is going to be many different neurons synapsing onto one soma, one cell body. And so we have many presynaptic axons and one postsynaptic, many presynaptic neurons and one postsynaptic neuron. So these types of events are also important in determining the degree of the signal. So for example, in divergence, because we're splitting that signal off, we may have a slight watering down of the degree of the neurotransmitter that's released and the degree of the postsynaptic potentials on these various neurons. Whereas we can also think about the opposite happening with convergence. We can think about many different neurons synapsing onto one soma. And so we're really amplifying or increasing the degree of neurotransmitter that's released and the degree of IPSPs or EPSPs that are generated on the postsynaptic neuron here. So divergence and convergence also play a role in determining if we get closer or further away from that threshold value. And then there's the idea of summation, again, something we talked about. We can add up different graded potentials if they're close enough in time or space. Temporal summation is if they're happening on at different times, slightly different times, but the same exact spot, okay? And so here we can see we've got EPSPs and IPSPs, and temporal summation means that they happen at slightly different time periods. So when we look at let's get this out of the way. When we look at the graph here, we see that we're only looking at synapse A, right? Temporal summation only takes one spot into account, the same space, different time. And so because we have one synapse coming in on at one graded potential coming in on synapse A, slightly separated by another graded potential coming in at the exact same synapse, because they're close enough in time, we can add them together. And as you'll see, we get enough of a membrane potential change to get to that threshold value and fire an action potential. So that's temporal summation. Spatial summation happening at different synapses. So here we're taking different synapses into account. We're looking at what's happening at synapse A, what happens at synapse B, what happens at synapse C, and they're happening at the exact same time. So exact same time, different spots for spatial summation versus the exact same spot, slightly different times for temporal summation. And as we can see, we simply add those different graded potentials together. And once again, we determine whether or not that gets us closer to threshold. The third mechanism here is frequency coding. So the degree of depolarization is really determined by the frequency of the action potentials. Because we have summation happening, this also affects the degree of depolarization, so how much of a membrane potential change we see at the soma. And so summation is another way to influence how fast those action potentials are coming in as well, right? Because if we depolarize to threshold and we're able to add those greater potentials together, we can get faster action potentials if we're getting closer to threshold more frequently, if that makes sense. So I'll say that in another way here. So summation can influence frequency of action potentials, because if we're getting closer to the threshold more frequently, because we're adding those greater potentials together, then that is going to generate more of those action potentials and more neurotransmitter, which is going to make a greater IPSP or a greater EPSP on the subsequent neuron. So summation is also feeding into frequency coding. And this is the idea that if we increase the rate of action potential firing, we increase the amount of neurotransmitter that's released, and we increase the degree of the IPSP or the EPSP on the subsequent neuron, which is going to get us closer to threshold on that neuron as well. Okay. And then the fourth mechanism of neural integration is called presynaptic modulation. And presynaptic modulation is pretty much regulating the synapse with a third neuron that's synapsing at that junction. And so it's not exactly influencing the membrane potential change. And so I don't want you to think about it as influencing the synapse in that way. It's pretty much influencing the presynaptic neuron and how much neurotransmitter is released from the axon terminal of this presynaptic neuron. So there are two ways that we can modulate the synapse. There's presynaptic facilitation, which will increase the amount of neurotransmitter released, or we can have presynaptic inhibition, which will decrease the amount of neurotransmitter that's released. And for this type of synapse, this is the axoaxonic type of connection here. So if you remember, we talked about different ways that neurons can synapse on each other. We had the most common type, the axodendritic, which is the axon terminal synapsing onto the dendrites of that postsynaptic neuron. And one of the mechanisms that we said was pretty rare, not as common throughout the body as some of the others, was the axoaxonic synapse, where both axon terminals are, well, not both, but one axon terminal is synapsing onto another axon terminal. And this is an example of where we see that axoaxonic type of synapse at the presynaptic neuron, and this is influencing presynaptic modulation. So let's look at some examples of presynaptic modulation. So let's look at presynaptic facilitation first. So presynaptic facilitation is basically where we increase the amount of neurotransmitter that the neuron is releasing. And the important thing that I want to point out here is that this neuron does not have a membrane potential change. So it's not releasing neurotransmitter itself. It's just affecting or influencing how much neurotransmitter is going to be released. And so we can see here in this example, so we've got synapse D, synapse C, and synapse C is being modulated by neuron E. So neuron E is going to increase how much neurotransmitter neuron C releases. And if we look at the graph here, neuron C on its own is a small graded potential, not enough to get to threshold. Neuron D on its own is, again, a small graded potential, not enough to threshold. Synapse E on its own is absolutely no change in the membrane potential. So this modulating neuron does not change the membrane potential itself. It has no influence on generating a graded potential on its own. But when we look at synapse E and C, when it's being modulated by neuron E, then we see that it's enough of a change to get us to threshold because neuron E is modulating or facilitating or increasing how much neurotransmitter is released from neuron C at that synapse. Okay, and that's an example of presynaptic facilitation. If we look at, for example, presynaptic inhibition, we see the opposite happening. So the modulating neuron here is going to decrease how much neurotransmitter is released at that synapse. So at synapse G, we have a small membrane potential change. At synapse F, we have a similar change in the membrane potential. But when we look at synapse H on its own, absolutely nothing, no change in the membrane potential. If we look at our synapse F plus synapse H, again, we see no change in the membrane potential. But if we look at synapse F and synapse G, that's enough of a change to get us to threshold because we don't have that modulating neuron. So that modulating neuron is just making it hard to fire an action potential. It's making it hard because it's decreasing how much neurotransmitter is released from that junction. So synapse H on its own has no change, but importantly, synapse F plus H has no change as well. So we're pretty much silencing or numbing down the effect of neuron H or synapse F, excuse me, because we decrease how much neurotransmitter is released from that neuron F. Okay. All right, and so looking here, we can compare the different types of synapses here again. We talked about the axoaxonic. This can either excite or inhibit a synapse. It's selective in that it's going to determine which synapse is being modulated, whereas axodendritic and axosomatic type of synapses are also excitatory or inhibitory to the postsynaptic neuron, and they're non-selective, right? They're going to either release neurotransmitter or not. It's not going to determine which synapse it's going to choose. It's either going to release neurotransmitter or it won't release neurotransmitter. And so it's non-selective the way that axoaxonic synapses are. We can see, if we go back to this slide, that the modulating neuron here can choose which synapse it's going to synapse on or which synapse it's going to modulate. And we don't see that with the other types of synapses, the axodendritic and axosomatic. And so here we're pretty much just summarizing these events. So summarizing what's happening here on this neuron. So neural integration, we said, is pretty much happening at the axon hillock. It's really taking a lot of different things into account. It's taking divergence versus convergence, right? The different signals that are coming into this neuron, whether they're being kind of watered down or whether they're being amplified. It's also taking frequency coding into account. How fast are action potentials coming down the previous neuron and arriving here, being translated via neurotransmitter release onto this soma. So frequency coding, I said, also is influenced by summation. If we're able to add graded potentials together, it's going to lead to more frequent action potentials because we're going to get to that threshold value more quickly, more sooner, more frequently. And so we're going to generate action potentials faster down the length of that neuron. It also takes into account the type of graded potentials. If it's an EPSP, it makes an action potential easier, more likely, more favorable. If it's an IPSP, it makes an action potential harder, right? It hyperpolarizes the membrane. It takes us further away from rest. It makes it harder to get to that threshold value. Or if we think about chloride as an example, it can also resist the membrane potential change and make it equally as hard to depolarize that cell. And so all of that's happening on the soma, all of that information is being registered. When we get to the axon hillock, all of that's being calculated or judged or assessed, so to speak. And then we determine the condition of acquirement if we get to threshold or not. If we do, another action potential is generated here. It moves down the axon and then it gets to the axon terminal and it releases neurotransmitter. And then the entire cycle happens again and again and again, okay? And so we can think about this as far as the presynaptic neuron and the postsynaptic neuron in order to understand the events that are taking place. But again, don't get so focused here that we don't understand that this is really a loop of events. It's a cyclical loop of events in that in some regard, the presynaptic neuron is also a postsynaptic neuron when we look at another synapse. So right, there's a lot of synapses happening. And so the presynaptic neuron can also be thought of as being a postsynaptic neuron. And the postsynaptic neuron can also be thought of as being a presynaptic neuron, because this is a sequence of events that's happening on several different neurons really quickly, and many different synapses occur throughout our entire nervous system. Okay.